to walk you through the event, introduce to the speakers, and where they have come all over from the world to share their knowledge and enhance our mental horizon. This is an initiative by our Aaivalayam team to bring expert researchers from across the world to share their knowledge to those who have keen interest to learn and improve themselves, especially in material science research. The online Raman spectroscopy masterclass is organized by a team of researchers from Center for Advanced Materials, which is a part of Aaivalayam. So Aaivalayam is a non-profitable charitable trust founded by Dr. Satish. Our motto is to extend the horizon of research to every human being, and the Aaivalayam is a powerful place to do research. The objectives of the Aaivalayam is to formulate a research organization which is dynamic, integration of academics and industries that are cooperative, productive, creative for the welfare and betterment of the society as a whole. We from Center for Advanced Materials are aimed at providing scientific training and skills to students to motivate them towards research by acting as a bridge between academia and industry. We also work with the community to spread awareness of career opportunities. At Aaivalayam, we also discuss the issues with the researchers, the transition between academic and industrial careers, those kind of things. So as you may have already know from the brochure, this is a two-day online event with researchers or professors from renowned institutions from all over the world. As for today, we have 3 resource persons: Mr. Kamalakkannan from University of Madras, India, Dr. Amudashelvi from Time Gate Instruments, Finland, and Professor Juan Manes from Universidad de Valladolid, Spain. So after each session, participants are encouraged to engage the speakers with doubts and questions, whatever they have, or their specific problem according to the research work, also keeping in mind that we have a time limit. So if you have more questions after the talk, about the talk, feel free to contact us to clarify your doubts. So also we are delighted to announce that we have a very special session with Dr. Joyce, Director of Center for Advanced Materials, who will give a brief introduction about Aaivalayam, who we are and what we do. So be prepared for that as well. So this program has already shaped up to be excellent, and the networking opportunities in this program will be indeed outstanding. So this masterclass provides a valuable opportunity for research scientists, research scholars, industry specialists, and decision makers to come and share their experience. I assure the participants will have fruitful and rewarding exchanges in these 2 days. So today masterclass is about more than 100 participants participating all over India. So, and some of them are from abroad as well. So I would humbly suggest all the participants to make sure that their audio is turned off during the talk. After the talk, you can turn on and ask the questions as well. So I would encourage all the participants to engage themselves in all activities and discussions throughout these 2 days in this Zoom digital platforms. So I wish everyone to have a successful, safe, and fruitful masterclass. Last but not least, I would like to thank our organizing team, Dr. Joyce, Dr. Satish, Dr. Surya Karthik, Mrs. Bibi, and Mr. Sandosh, and the speakers who have come from all over the world. So with this note, I would like to pass on to Dr. Joyce to welcome the speaker. Hello, ma'am. Good morning.
Yeah, can you hear me? Am I audible, James?
Ma'am, yes, ma'am, but it's quite low. The voice is very low.
Okay, 1 minute. Okay, good morning, one and all. I'm Joyce. It's a pleasure to have you here for the masterclass. Maybe I wish you everyone to be involved in every session. So I strongly encourage the participants to ask any doubts or things that need to be clarified now and then, so that you will have the complete benefit of the masterclass. We have designed the class to be engaged every time. We also have organized adequate intervals in between, so that you can relax and have clear mind and come for the next session. So this is really a good opportunity for you to explore much about Raman spectroscopy. So please be involved and engage yourself. Thank you very much for your participation. I would like to introduce our first speaker, Mr. Kamalakkannan. He completed his master's and Master of Science and Master of Philosophy in Physics from School of Physics, Madurai Kamaraj University, and currently he has already completed his PhD in the field of nuclear physics in Department of Nuclear Physics, University of Madras, and he is waiting for his defense. And he was awarded the JRF and University Research Fellowship by Department of Atomic Energy. He has very specialistic knowledge in spectroscopy, especially positron annihilation Doppler broadening studies for the analysis of the defects depth-wise. So he has published many research papers on radiation implementation effects of silicon carbide materials by Raman and also positron annihilation. We are delighted to have you, Mr. Kamalakkannan. Please go ahead. I would like to hand over the platform to you. Thank you very much for your kind agreement to be a part of this Raman Masterclass. Thank you very much.
So, very good morning to all. Am I audible?
Yes, sir.
Yeah.
Yes, sir, you are audible.
Okay. So, thank you so much for your great introduction about me. Actually, I am very happy to be a part in this Aaivalayam and deliver my talk in the Raman spectroscopy relative thesis. So, my presentation in this particular talk is designed in the basics, okay, of this Raman spectroscopy and how we can analyze the materials for the different things, which means how we can study the defects oriented things and some character table and what is the basis behind that one theory. Okay, that's my talk of these things, and I share my slide. Okay, you can go on the particular one, right? So is it visible now?
Yes, sir, it's visible.
Okay, fine. So,
Yes.
so how we can analyze the Raman? Okay, so that's the thing. So starting from introduction to the profiling. So that's my content of my talk. So you know very well about the Raman spectroscopy. So it's an Indian scientist who discovered that things as Sir C.V. Raman. So mostly people are using to study the molecular structure by using the Raman spectroscopy. So not only that, but Raman's tool is a very good tool actually to determine most of the things as not only the atomic structures, which means from starting that things as to we have to study the defect profile and defect analysis and carrier concentrations, and as well as the quantification of the defects also we can identify. So it's one of the very good tool actually. Okay, so you know very well. So what is the basics of the Raman means? We are giving the radiation, which means from the outside monochromatic radiation is incident on this particular sample, and it is scattered. Okay, so the scatter is different completely. That's all. So if incident energy is somewhat E na, so that the scatter energy is lesser than that particular wavelength or particular energy or is lesser than energy. Okay, so that things is actually we have to study. So we are giving the some energy and we are observing the some other energy. That's all completely. So that's the things we have to study in this particular way. Okay, so you see the incident radiation is falling on the sample and it is scattered. So most of the light is scattered, which is equivalent to the incident energy or incident frequency. So that's simply called the Rayleigh scattering. So if the scattered wave energy is lesser than the particular instant rate, that's called of course it's inelastic scattering. Something it's called a Stokes line, and if it is higher than that things is actually that's called anti-Stokes line. Okay, so that you know the basics of that one. So of course, so we are concentrated on the Raman scattering, which is inelastic scattered lights only. We have to concentrate it, right? So which means so of course, so incident light is comparatively is nu zero means, so it's maybe higher than the incident light scattered means it's of course that's anti-Stokes. So that we are considering the Stokes line, which is lesser than the incident rays. So that things is defined here, of course. So yeah, electrons of course it's molecules which oscillated with respect to the instant energy light. Okay, if electric field is given this particular things, of course the molecules of the atoms is also oscillated with respect to the applied electric field. So even instant light is also having the electric field. So because of that instant light electric field, the molecules of the samples is also oscillated with respect to the instant light. So that oscillations gives the change in the polarizability because P equal to alpha into E. So and the polarizations also changed. So change in polarization gives the Raman spectroscopy. That's typical nodes. I think that things you know. So I started from that the basic theory behind that one. So of course molecular spectroscopy having the 3 energy states. I think you know, right? Starting from the rotational energy level and vibration and electronic energy level. So rotational energy level is the least energy, you know, something. So which means if the molecular is transient between the rotational energy levels, and of course the spectra which is in the range of microwave regions, and so at that time both the electronic energy states and vibration energy state are in the ground level. Consider that that's the ground level, and if the transition happens between the vibration energy levels, so vibration energy levels it includes the rotation energy levels also. So that's in the spectra, the outcome spectra is in the region of infrared region, and if it is electronic energy transition, that gives in the visible region. We are concentrated in this particular vibration energy level. So in this vibration energy level transition gives in the IR region. So this consists of the Raman and infrared spectroscopy. So both the things comes under in this particular vibration energy transition. So the major difference of the Raman and the infrared spectroscopy means it's a change in the polarization, and for Raman spectroscopy is change in polarization, but IR spectroscopy change in dipole moment. So that's things as you know. So the basic theory behind that one. So just we are considered that the diatomic molecule. So consider that it's a rigid diatomic molecule which having the mass M1 and M2 shown here, and the center of mass of this particular one is pointed as G. Okay, so consider from mass 1 to the point G, which radius is R1, and R2 is the mass 2 to center point, and the interatomic distance. Okay, that's called consider that R. Okay, if it is rotation distance, of course it having that moment of inertia. That moment of inertia is formulated as I equal to m r squared, where r is the bond length. So that moment of inertia, I mean this mass is simply a reduced mass because the diatomic molecule we are considering. So that if it is rotating now, it's also having the angular momentum. That angular momentum is also quantized. So where L equal to n h dash, that n can be written as square root of j into j plus 1 h divided by 2 by, right? So that j is the angular momentum quantum number. Okay. So from that case, we can calculate the energy of that things. So which is E equal to half a omega squared. So if you substitute that I and other values in particular things, it gives j into j plus 1 h dash squared divided by 2, right? So of course the selection rule for the any typical spectroscopy, Raman spectroscopy is plus or minus 1. So for that case, if transition happening from j to j plus 1, so I am calculating the frequency for that particular things, which is delta E divided by h. So this can be written as j plus 1 to j transition. So the final result is gives like that j plus 1 h dash divided by 2 pi I. Okay, so in this case, we know, I mean, we want to identify the frequency. So if we know the moment of inertia value, or if we know the frequency change, okay, that things, we can easily identify the R value, which is called bond length. Okay, so if bond length you can identify, now we can identify most of the important properties of the molecules, such that the what type of molecule and symmetry and structure, everything. This is typical example for that particular things. So our aim is to calculate the change in frequency, right? So so this is the classical theory for the Raman spectroscopy simply. So any molecule, okay, so which is experience a polarization if it is applied to the external electric field. Similarly, the light rays which having the electric and magnetic field, both it have that particular things. So if the incident rate have the electric field E, so it's considered that E0 cos omega t, where omega equal to pi nu naught. So because of that applied electric field by the incident light, the molecules is also oscillated with respect to that applied electric field. So it experiences a polarization. So that polarization is represented as the polarizability of the particular things can be represented as alpha equal to alpha naught beta into cos omega t, where omega is that after polarizability it's happening, right? Where alpha naught is the equilibrium polarizability and beta is the rate of change of the constant, right? Polarization constant, right? So if we substitute this particular value for the polarization formula P equal to alpha into E, it gives three different frequency components. So simply, so one is equivalent to the applied radiation frequency, and another two is greater than that particular frequency or less than that particular frequency, applied frequency. So if it is greater than the frequency, in the sense its energy is very higher compared to the incident light, simply it's a Stokes, anti-Stokes line, sorry, and nu naught minus nu m, which is lesser than frequency, it's a Stokes line compared to the incident line. So we have to consider these two parameters. Simply it's inelastic scattering, it gives the Raman values, right? So how much is the frequency shifted from that particular things, we can identify the R value and other things. If there is no beta value, which is called there is no change in the polarizability, now of course this parameter will not comes. So change in polarizability is 0, the Raman spectrum is not observed. Okay, so no Raman lines observed, the polarizability beta is 0. Simply it's a classical theory. And quantum theory, so that's fine, that's easiest one. So of course the energy is greater than the incident light, so simply it's anti-Stokes line, and is lesser than the things on Stokes line. Okay, finally this is some basics of that one. So right, so Raman and IR both will come on the vibration level. So what are the major difference means, it's a scattering principle which is Raman, and it's absorption which is comes under the infrared spectroscopy. As already we discussed, change in polarizability is gives the Raman active modes, but in IR spectroscopy is change in dipole moment of the molecules, right? So anyway, so the homonuclear molecules are homopolar molecules such as hydrogen, are mostly homonuclear molecules or CO2 molecules. Okay, so this doesn't have the what is the dipoles in this particular one, right? So if you apply that any electric field, now of course it is polarized. So homonuclear molecules mostly it gives the Raman, but homonuclear molecule it does not respond to IR because it don't have the dipoles in this particular case. So consider this example. So this is the homonuclear molecule, example of CO2, carbon dioxide, right? The carbon is center, oxygen. Okay, both the sides is given this way, right? If it is symmetrically stretched, which means it's both the molecules, both oxygen molecules is stretched in the same directions, I mean in the same way, symmetrical stretch in this sense, the change in dipole is not observed, okay, because the net dipole is 0, because both the molecules are vibrated in the same direction, I mean same way. It's one is opposite, another is opposite, na? So both the net dipole is 0, so change in dipole is 0, so that it is IR inactive, right? So but it's actually polarized, which means the separation of that particular things is, which means atoms are separated, simply it's polarized Raman active. So symmetry states most probably for the carbon dioxide gives the Raman active modes. So and similarly in the asymmetrical stretch, so consider the two oxygen atoms is fixed and carbon atom is moving, okay, something like that. So if it is moving now, of course one is what is that? One side, I mean the net dipole is, of course we have to see the net dipole. The reason is one is different value and another is different value. If net dipole is, of course the change in dipole is occurring this one, but polarizability is not changing this case. So if asymmetrical stress sense, the IR is active because dipole is changing, Raman is inactive in this case. If it is bending, so consider that the bending is happening in the top to bottom, so it's towards us and behind that particular laptop. So two types of stretching is happening, but both are in the same energy values only. So it's a degenerate case because same energy states only is happening in this one. So if you are calculate the net dipole moment, so this is in the top and bottom in the sense means you have to separate this component in x-axis, y-axis, sine and cos theta. Of course the net dipole moment is happening. So the change in dipole is occurred, but change in polarizability is not occurred in this case. So that IR is present for the bending and Raman is inactive for the bending cases. So most probably symmetrical stretch for the carbon dioxide is gives the Raman lines, right? So which is some principle is there, which means so IR and Raman spectroscopy, so both are complementing each other for the centrosymmetry molecules. So this is called mutual exclusion principle, which means if centrosymmetry molecules we are taking that like H2OCO2 and C2H2 means, so where I mean the lines which is active in the Raman, the same lines is not active in the IR and vice versa, okay. So this principle is simply called mutual exclusion principle. So most probably for the centrosymmetry molecules only. The non-centrosymmetry molecules is maybe obey the both Raman and IR things. So for the centrosymmetry molecules we can observe that particular one. And sorry, it's muted. Okay, fine. Right. Next. So I have to introduce in the symmetry and character table of the system. So that's important in this particular section. So the previous part is just introduction of that. Simply symmetry, you know. So both the sides, which means if you draw a line, so both the sides will be equal. So mostly there are 5 symmetry operations is there for a molecule in the point group symmetries. So these are the identity, which is called nothing. The same molecule will be represented, and rotation about an axis. So if you are rotated, the particular things is means the same the symmetry elements will be obtained, and reflection about a plane. Okay, so it's a plane. So you have to place the plane, and the same molecule will be observed. And improper rotation, which is rotation followed by the reflection, or reflection followed by the rotation, and inversion. Okay, so inversion is through a point. So simply it's a point relative things. So the inversion is not shown here. Simply, so consider a triangle for this case. So we draw a line like this, okay, from top to bottom. So actually this is the what is that? Twofold symmetry, which means it's a C2 axis completely. If you are rotated in this particular system with respect to this particular axis now, so 180 degrees is enough to get the same system. And another axis I can take, so which is passing through the triangle. So that's C3 symmetry, which means it's going towards this particular triangle in the sense, okay, if you rotated that particular system, it gives the 120 degree rotation is enough, because it's a threefold rotation in this case. So 360 divided by 3, in the sense it's 120 degree. So if I rotate 120 degree, same structure will be obtained. So choosing the axis for the rotation is very important, which means if I draw a line like this, so top to bottom, in the sense it gives the twofold rotation, and similarly if I draw a line in the perpendicular to that particular threefold rotation. So that is the rotation. And mirror plane, which means the reflection, in the sense I just place a mirror. Okay, suppose if I place the mirror in this particular axis, top to bottom axis, right? So what happens, the left hand side is reflected in the right hand side, right hand side reflected left hand side. Okay, so this is one of the symmetry plane in this particular one. So which axis we have to choose, that's the second case. So simply this is the some representation of that symmetry elements of the system. So directly I have to go that table for which is from these things we can calculate the Raman. So I am taking the C2V symmetry point group material. So simply, which is, for example, it's a what is the water molecule. It's a C2V symmetry, which means it's a twofold rotation, and V is the mirror plane. Okay, so these are the symmetry operations which we done. Okay, so these are the symmetry elements which is available in this particular one, where E is the identity, C2 is the twofold symmetry, and sigma V is the plane, okay, which is placed in the xy axis, right? And sigma V is the mirror plane, which is placed in the YZ. Okay, so just I introduce, and furthermore the parameters, these parameters, what is the representation, I will tell in the next slides. So there are totally 4 symmetry operations, so that we have to put the order of the group, which is h equal to 4, and functions. So what kind of functions I have to do? So z is the translation along the z axis, right? And a1, a2, b1, these are the some kind of symmetry labels. Okay, so this is the Milligan symbols. I will explain this in the next slides. And yeah, and the numbers which is denoted here, 1 and -1, like this. So one is the if I do some kind of operations like this, so suppose consider that x and ry, in the sense x is the translation in the x-axis and rotation in the y-axis. So if I done these operations, so whether the molecules is changed its position, like if it is reversed, it's -1. If it is not reversed, the same structure only obtained 1. So that is the number representation. So this is from this table we can calculate the what kind of modes will be present for the Raman, and what kind of modes will be present for the IR things. So usually from these functions and quantity functions also we can identify somewhat the Raman and IR active modes simply. So in the sense the functions, the translation functions x, y and z, okay, these are related to the IR spectroscopy, and rotational things and quadratic functions mostly. So this is related to the Raman active modes simply. So but we have to calculate the reducible representation. Finally we have to determine that particular one, right? So see, I am taking the C2V symmetry point groups. So for example, water molecule, so H2O, right? So that molecule is shown here simply, and it's have the twofold rotation, that's already we discussed it. So consider the oxygen atom. Okay, so the axis is represented here, so x-axis and y is z. Okay, so suppose this is the C2 symmetry of that. I am taking the axis in the C2 symmetry point. So consider the 2px orbital. Okay, so I'm rotating in the C2 axis of the oxygen molecule. There's the x-axis p orbital structure. Okay, the plus and minus will be there. So after rotation, so this will be interchanged, which means 180 degrees changed. So minus will come here and plus will come here. Okay, so what happened? So it's a 180 degree reverse, in the sense I have to put the -1 for that case. So C2 symmetry, I have to put the -1. And similarly, identity always is 1 only, because same molecule we have to represent it. So no position changed, molecule position is not changed, but actually it's reversed, so that we have to put -1. If molecule position is not changed and as well as it's not reversed, it's 1. If molecule position is changed, we have to put 0. So I am not considering that hydrogen molecule, I am considering the oxygen molecule only. So effect of the oxygen molecule 2px orbital, so it must be -1 for the C2. Similarly, I have to put a xz plane for the mirror. Okay, so this is the xz plane. So it's almost it's a plane of the particular one, right? I'm cut this H2O molecule in the axial wise, which means in the plane of that particular one. What happened? The same things is reflected. Nothing will be changed. Okay, no reversible we can observe. So if we put that xz plane of the mirror, okay, so that I can put directly 1 because it's unaffected. If I put YZ plane like this, okay, YZ plane, this is the plane actually. So it's just to cut the oxygen, okay, exactly. That plane is cut the oxygen. So what happened? This plus is reflected here and minus is reflected in the opposite direction, right? So it's actually reversed, so that we have to put -1. Similarly, for the 2py oxygen orbital, so what happened? I have to what is that? So this is a plus and minus, okay, like this in the oxygen oriented things. So similarly, this one is like that, okay. So this is the oxygen, this is a plus and minus, okay. And what happened? I have to rotate these in the z axis, along the z axis. So what happened? This plus will become reversed and minus will become reversed in this direction. So of course in C2 symmetry it will become -1, but in the sigma plane, okay, you can observe that particular things is it's changed -1 and sigma v dash YZ plane 1. Similarly 2pz orbital, you just consider the 2pz orbital is a z plane, the plus and minus will be there. Even though if you rotate, no position is changed, it's always 1 on 1 everything, right? So similarly we can observe so where will it come 1 and where it's not come 0, where it come -1. So next you can see, so in the translation, okay, so first we have to see that rotation, we have to see the translation of this one. So x-axis simply if it is translated like this, okay, I am rotated that particular molecule in the z-axis. So what happened? This x will become moving this opposite side, but actually the rotation is reversed. I mean the translation is reversed after the rotation. So if it is reversed, we have to put -1 for that case. And similar sense in the rotation in the y-axis. So depends on that particular value variations, whether it's 1, whether it's -1. We have to combine the results with respect to the different symmetry operations. So finally we have to combine all the results with a single table, which is which you saw in your previous slide, okay. So this is the finalized things which is completely represent all the modes. For example, if B1 doesn't, so I am translated x-axis, rotated in the y-axis. So whether identity is always is not changed, but it is reversed. C2 axis and sigma v is not changed, sigma v dash is changed. So everything is represented in this case. So here we have to mention that A1, A2, A3. So what are they? So we can see here. So that simply is a notation. So that notation which stands for A is the symmetric with respect to the principal rotation axis, and B is the asymmetric, okay, in the rotation axis completely, and E is the doubly degenerate because of bending, okay. You know that. So carbon dioxide molecule, if it's bending in the top to bottom and front to back, in a sense both are the same energy levels only, okay. So nothing will be new things. So same energy but different bending is there. So it's a degeneracy, okay. That's representing E, and T stands for 3-dimensional representation, okay. Here A1, B1, E1 like that, A2, B2, if mention that 1 and 2 in the sense that 1 is the symmetric and 2 is the anti-symmetric. And in some cases in sigma in the plane which is perpendicular to x, z, y, z axis, is they give primes, okay. The single prime is symmetric and double prime anti-symmetric. In some cases we can see G and U, so that is G is symmetric and U is the asymmetric simply. So which is usually mentioned for the centrosymmetry molecules, mostly they have to use that particular one. So you can easily identify that particular Millikan notations, so where what it stands for these things. For example, in the 6s SAC materials, the H is the hexagonal, SIC is silicon carbide material. You can see the irreducible representation is around A1, B1 and E1, E2, around 4 into 6. So 24 peaks we make maximum we can obtain this particular one, right? Then E is the degeneracy, as you know, right? So it's a C6V symmetry. So these symmetry tables you can get from any books actually, okay. C2 symmetry, C6 symmetry table, character table, it's available, and the complete structure you can get it. Fine. So next, so how many Raman modes usually we can see, or IR modes usually we can see, right? So if there is n number of atoms, so the degrees of freedom can be calculated, maximum degrees of freedom, so 3n, okay. If three molecules for the hydrogen H2O in the sense 3 into 3 is 9, so 9 degrees of freedom will be there usually. So for linear molecules, so number of constraints we have to neglect that. It's for linear molecule 3n minus 5, for the non-linear molecule usually 3n minus 6. Of course H2O molecule is a non-linear molecule, so 9 minus 6 around maximum 3 vibration modes we can observe. So in some other case we can identify NC2, that's the in classical mechanics you can identify that number of constraints can be calculated by using the NC2 formula. So even you can apply the here is also that's obeying things, right? So how we can identify that gamma modes, irreducible representation of the gamma. So consider the H2O molecules, which is represented x, y, z axis shown here. So I am following this one. So see, so for that case, actually there are totally 9 degrees of freedom, so that I am taking the 9 cross 9 matrix completely. So for identity, so the complete things, I mean molecules does not change its position like +1 -1, so that every trace of that matrix gives the one value. For example, what is that in the sense? So just identical molecules completely. Simply I am doing I'm nothing, same molecule we have to represent it. So for example, from C2 onwards you can understand easily. So this put -1 here in the trace of the matrix to 3 elements -1, other element 0 0 in the sense 0 in the means the atoms are displaced, okay, and -1 in the sense this is reversed and +1 is not reversed completely. So you just see, so this is the every representation is the x axis in the oxygen and y axis in the oxygen, z axis in the oxygen, like that. And here is also the similar way, 9 cross 9, okay, simply 9 degrees of freedom completely represented. Okay, so let's see. Suppose so I am rotated in this particular H2O molecule along the z axis, okay, in the C2 symmetry. So if I rotate in the sense, x axis will become reversed and it's come in this opposite way, which means in our left hand side. So I have to put the -1. And other cases you just to see the hydrogen is the first hydrogen will become in the position of the second hydrogen, and second hydrogen will become position of the first hydrogen. So actually this atom is displaced, so that we have to put 0. The other things will become 0. Just we can see, right? And similarly, if I rotate these things along the z axis, what happened to y? So y is also reversed, so that we have to put the -1. And if I consider the jet oxygen, so nothing will happen because this is the axis of rotation, so it's not reversed completely, so we have to put 1. Okay, so if I rotate the things, all other atoms will become 0. So I just simply which means the position is displaced, and where it will be there in the sense you just to see here. So if I rotate so x axis in the hydrogen atom in the position B na, okay, so it will become in the A axis, okay, if position B to A it's moved and also reverses, so that I have to put the -1. So but our aim is to find the eigenvalue of this matrix, so only trace only is important, right? So the trace of this particular matrix, just add everything completely, their x will become 9. So for that case, if I add these things, x will become 1. Similarly, we have to identify sigma v and sigma v dash, where along y z direction and x z direction. So that values gives around 3 and 1. I am not represented in the matrix of sigma v and sigma v dash, just I am directly put that things as, right? Then E will become 9 and C2 will become -1, sigma will become 3, sigma v dash will become 1 from the matrix representation. And finally, we have to break these gamma modes into its individual components, okay? So in irreducible representation, how we can identify that one? So which is the formula is related things, 1 divided by h summation over number of operations. This is from the symmetry points from the character table, which we put 1 -1 -2 like this in the scatter table, that value. And from the matrix you have to put that 9 -1 3 1 like this one, and this one I am taking the 1, which means I am calculating the irreducible representation of the number is 1. So completely, where h is 4, we know, because the number of operation I mean the symmetry operation is 4, so instead of h I have to put the 4. So if I use these particular things for each and every E, C2, sigma v, sigma v dash, I can easily calculate the components of the irreducible representation. So just you can see in the next slide. So for the A1 mode, so for these things, as you can see, for A1, this is the characters which is available in the table, okay, 1 1 1 like this. So all things are 1 and h is 4. So similarly, I can substitute this value 1 by 4, and all things are, the green lights are also 1 for every character, and 9 is from the matrix, okay. So is a E, this is for C2, this is for sigma v and sigma v dash. So everything is substituted and it gives the 3A1. And similarly for the number A2, the second point, so 1 1 -1 -1 simply. So 1 and 1 -1 -1. So similar way, if you calculate the final result, it will gives 3A1 and 1A2, 3B1 and 2B2 completely. So the total modes which is available in this particular one is called 3A1, 1A1. Completely, if you add everything, it will give the 9 irreducible representation. So it's a total degrees of freedom. Of course, we determine 3n minus, 3n total degrees of freedom is 9. Of course, it gives the 9 value. But we need to calculate the vibration only. So for what that we have to subtract the gamma modes of the translation and rotation, because we need the vibration. Okay, so from the total modes, I have to subtract the rotation and translation. So for that case, simply the vibration which is equal to minus rotation and minus translations. Simply the rotation and translation you can calculate by using this particular table. Simply, so this is Z is the translation symmetry. Simply, so what happened? A1 is translations obeying and B1 and B2. So these things I have to subtract. So simply you see translation of that representation of this one. So A1, B1 and B2, these are the translation, and rotations also R, represent R, A2, B1, B2. So I have to subtract these two values from the total value. It gives the 2A1 plus 1B1, right? So completely there are three vibrational modes we can obtain. So this is also obeying that 3n minus 6 vibration for the nonlinear molecule. So for the vibration modes of the H2O molecule, there are only 3 vibration modes which is available. So that 3 vibration mode is also applicable for the IR spectroscopy, because it's a non-linear molecule. If you consider that linear molecule, so only one Raman, other things are IR spectroscopy. But for non-linear molecule, so both things will be things. We discussed this one. So Raman plus IR both are presented in this one. So that's all. This is the identification of the particular representation, how many modes will be present in the Raman and IR. So after spectroscopy, so these things is just IR spectroscopy is absorption between the vibration energy level, and Raman spectroscopy is so we are giving that energy, it's going in the some virtual state. That virtual states must be in between the electronic states, okay, in between the electronic states. If it is more than that, of course it is going in the UV visible fluorescence. So what happened, we have to choose the correct laser which is optimum, which is opt for that particular material. So if any impurities or any kind of doping, if you are added that particular things, of course fluorescence effect is also available, because in between the states some kind of energy states available. It can be shifted, de-excited in between that particular things, which gives the different broad peaks and broad features of the IR level. Okay, so so you have to choose your lasers particularly exact way to determine the final result. And so this already we discussed it, because Stokes and anti-Stokes lines of the Raman, and of course our giving laser must not exceed the electronic levels. So this everything is represented in the single way, which means pre-resonance. After pre-resonance you will get the fluorescence most probably. The reason is the excited electrons may de-excited in between the upper state rotational levels or upper state vibration levels also, which gives the fluorescence. Where the fluorescence peaks is actually it's completely a broad nature, broad features, that's unavoidable. Okay, so that for that case you have to choose the correct laser. So consider so this atom, this molecule, so 514 nanometer we are giving and 785. So consider that 515 is higher energy. Okay, so what happened, it is going up to the excited level and it gives the fluorescence nature, it's completely broad features only, we can't observe nothing, right? And if 785 it's a lesser energy compared to the 515, of course it may go up to the virtual state and come back, which gives the Raman lines, so such one particular one. So lasers must be chosen. So of course whether I have to choose any laser which is lesser energy, okay, that's also somewhat difficult. So for that case you can see this is the absorption of the material. Simply 632 is lesser energy compared to the 514. So whether I have to give the 514 or 632 so the result you can see here. Okay, so if I took 632 nanometer of the excitation, in the sense it gives the broad feature of the system. If I take the 514, which is almost near to the absorption of that material, it gives the more number of Raman modes. We can see more number of Raman modes, which means clearly it's visible. So the lasers must be almost in between the the electrons must be excited in between the electronic states, as well as it's almost near to the absorption of the system. You will get the better Raman modes most probably. Right. So what kind of things we can identify by the Raman spectroscopy? So of course I am telling here is a very lesser only. Of course we can identify more number of things, but most probably the intensity is related to the concentration or what is the orientation of the molecules. That's mostly it's represented. And if it is broadening in the senses, of course it is the disorder, structural changes and everything we can determine, because if it is any impurities levels is available, in the sense, of course, in between the states is also some changes will be happen, so that the peaks will be broadened usually. And if it's shifted, stain happening, okay, so because of that applied disorder, stain and everything we can determine. So not only that, the frequency shift is also tells the carrier concentration, especially the localized carrier concentration you can identify. Even Hall effect measurement, you can't identify the localized value because it's a bulk value only it will give for the some kind of area, but in the particular laser spots level only you can identify the carrier concentration by the shift of that particular frequency, right? But which frequency, which mode you have to choose, that's important. And the laser is must be, the Raman spectroscopy must be in the confocal nature, so that we can identify very easily in this one. And this is a typical instrument, so laser is given and it is scattered by the sample, and the scatter is observed in the different directions. If confocal Raman spectroscopy if you are using so the laser is falling and it's observed in the same direction, which means the same points only you have to observe. So one of the benefit of the confocal Raman spectroscopy, you can use this for the jet scan facility, which means depth wise you can analyze by using this confocal spectroscopy. So that's a very good advancement of the Raman. So this is the typical components we have to use. And there are more number of lasers we can use in the Raman analysis. So mostly which one is near to your absorption wavelength, you have to choose that particular one to identify the different modes here. Okay, so that's things. And of course we can identify more number of things, most probably for the strain and carrier concentrations, and qualitative measurements of the disorders also we can identify. And quantification also we can done it. The measure of disorders also done it by using this Raman spectroscopy technique. So in the previous cases we are discussing about the first order Raman scattering only, because it's obeying the selection rule. I already mentioned plus or minus 1. The second order Raman scattering is also very important to determine the structural changes for the system. So it's simply a 2-photon excitation, so that it doesn't obey the selection rule. So but it's usually weak, but these parameters also gives the very good information of the disorderness of the system. And of course, so what is the jet scan facility in the sense? Depth profiling, which means so this is simply confocal Raman spectroscopy based things. So we are sending the laser and focused on a particular point, and it is reflected back, it is scattered back in the same detector, which means it's detected the what is the scatter light comes from the focal point only, and out of focus it's not detect that particular things. So for that case, the numerical aperture of the lens and spatial resolution and resolving power is always must be very high, then only we can identify. The typical value of the spatial resolution is, the depth resolution is around 0.5 micrometer most probably, and the numerical aperture around 0.9 is will be good to determine this jet scan analysis of the defects. So this is the Raman spectroscopy for the silicon carbide material. So it's mostly it's a first order Raman spectroscopy and enhance these things. Around more number of first order Raman spectroscopy you can observe. Mostly E to TA and E to TA both are combined together. If instrument is not good that much, you can identify, you can separate these things completely. It will be merged and forms some kind of broad peak like that. So most probably these Raman spectrum is aligned like these, starting from the transverse acoustical and longitudinal acoustical and transverse optical and longitudinal optical, and second order most probably after 1200 you can see mostly in the optical branches will become. So this is the arrangement, so you can easily identify that particular one. Simply see, this is the Raman spectroscopy for the irradiated silicon carbide material, which means we are implanted the nitrogen ions. So of course implantations break the bond between the SiC and gives the more number of homonuclear atoms, so that the homonuclear vibrations gives the broad feature completely, you can see. So from the precision value to the SCN 15, which means the 15 dose rate, and if dose rate increases completely the peaks completely disappeared, which shows that the amorphous nature is increases. Of course, if a body is, broadening is of course the amorphous nature, and the amorphous we can identify. And second order Raman is also enhanced very, very huge compared to other things. And after annealing, we can see that the homonuclear vibrations is almost suppressed, not disappeared but almost suppressed. Okay, so the disorderness also identified by using this particular technique. And as well as you can see, if the dose rate is increases, in the sense completely we can't be able to identify the characteristic peaks, prominent Raman peaks, but instead of that, things as amorphous, deformed, and homonuclear vibrations and CC vibrations, even carbon vibrations, which is in the second order region, this is also increased and it's shifted towards the lower region. Okay, so this is sp2 hybridization. So what kind of variations is observing from these CC modes also you can use to identify the how much it's damaged. Okay, so that's also identified. And after annealing, so you can see the modes reappeared, but the completely is not recrystallized. Amorphous behavior is completely still exists. So furthermore, this is a implanted sample, which means so the particular energy we have to implant, the sense it will be deposited in a particular depth. Okay, so that we have to define that where it's most of the damage is happening. Okay, whether it is a surface or whether it is a deep region. Of course, the atoms are mostly is damaged in the particular depth where I implanted. Okay, that we can identify by the Raman simply. So some no other techniques will be identified this much level. Even Positan can identify, but after that, this Raman is one of the good technique, easiest technique to identify the variation of the damages at a particular depth. We can see. So this is the bottom one is the sorry. So in the SN15 sample, this is the surface value. Okay, then after that, the after 1 micrometer depth, because the implanted region is below 1 micrometer. See, from surface to, if I approaching to the 1 micrometer, the intensity of the peaks is decreases, but instead of that, the amorphous peaks is also increases. You can identify that particular things as so the Raman intensity is decreases at 1 micrometer. And similarly, after annealing, we can observe that at 1 micrometer, the intensity of the crystalline peaks is increased up to 4 times. Okay, you can see, but in a surface it's very lesser. Okay, so which means the damage is created at 1 micrometer, even though after annealing, so recrystallization induced at a depth, but defects is migrated towards the surface and accumulated there. Okay, so that we can observe that some small broad peaks in the surface, but not in the deep region. Similarly, we can observe that in the 16 sample, high dose sample, nothing is there. Okay, in 1 micrometer depth, so the intensity is very less compared to things as right. So now after annealing, we can see the intensity increases compared to the surface, which means the migration of the defect. So similarly, we can identify, even we can identify up to 0.5 micrometer, 1 micrometer to 2.5. Like this, we can scan that material from surface to the bottom. So it's a very good information we can get it. What is the changes and where is the most of the damage is created, and behind that. Okay, so after 1 micrometer, what is happening? This one, that's also we can identify. Okay, after 1 micrometer, that's we are approaching the undamaged region. Of course, the intensities must be high. So that things as you can see here in the next slide. See, this one is the surface one, the bottom one, and after that at 1 micrometer the intensity decreases, even though it is 4 times enhanced, but intensity decreases compared to the surface one. So after that, if I am approaching 2 micrometer, 3 micrometer, now intensity increases because we are approaching the undamaged region. Okay, so after annealing, you can see here, so the surface region, the amorphous peaks is also still there because of the accumulation of the defects. But if you are approaching 1 micro, 2 micrometer, the intensity tremendously increases. So at 5 micrometer, because undamaged region, of course the intensity is equal to the pristine value, which means undamaged values is almost equal to particular things. So this is the typical first order, second order. I mean, first order is not shown, the second order, third order things. So of course the second order is lesser than the first order, right, and third order is way lesser than these things. So you can identify that thing. Mostly after 1000 frequency, you can see that the second order, 1200, you can see the second order, third order optical branches. So next, so that as I already mentioned, so after annealing, so the intensity is increases tremendously up to the pristine intensity we can reach it, and for the depth profile of the Raman. And of course here you can see the low dose sample at 1 micrometer and 16, I mean high dose sample at 1 micrometer, both are is coincident the same point, which is this is the measure of damage. So the the normalization of that particular things is damage normalized. So it's saturated in the 1 micrometer, which means so all the most of the bonds are breaked and amorphous saturated. Simply after annealing, we can change the variation recrystallizations by using using this particular Raman mode. So I am choosing these data from the A1LO mode. So we are interested in this A1LO mode in the sense it's a Langston optical mode which is highly sensitive to the carrier concentrations. So if carrier concentration increases, in the sense this A1LO mode of course is shifted towards the higher frequency region, and how much it's shifted that you can identify it, and you can given the further data, I mean you can identify the carriers, how much carriers you are concentration of the carriers, you can identify the particular localized depth. So we are implanted in the sense we know the how much dose we are giving, so we know the carrier value. So by LO shift we can identify whether it's matched with the theoretical and this experimental things. Of course it's a very good values we can obtain these things by using the Raman A1LO shift only. So A1LO mode you can identify by giving the polarized and depolarized Raman peaks. Of course the Raman lines are given in the laser lights, laser is fall in the jet axis, and it is observed in the jet, and of course it's it is polarized in the x-axis and observed in the y-axis. So A1LO mode completely suppressed. So this A1LO mode is a polarized mode completely, and other modes you can see E2TO mode, other modes is not suppressed completely, which means it's almost it's vibrating in all the directions. So depolarized light only we have to observe. So similarly you can identify so all other modes. So which one mode is completely suppressed with respect to the carrier concentrations, that you can identify that particular mode. You can fit it and get the values for the empirical formula. You can derive it from the origin itself, and the carrier concentration you can easily identify the quantification. Right. So so all the data which is shown here is area normalized, because to get the particular peak, even second order peak it's not visible completely, so that we have to give the more number of accumulation time, more number of power. So laser power is increased to more number of variations we have to do it to get the particular peak, so that we have to normalize that particular one to compare the first order and second order. So first order taken separately, second order taken separately, we can merge together in the sense we have to normalize that one. So area normalization is the correct one for that case. So we have to use the peak width software for the area normalization and background subtraction, and we have to compare it, and completely we have to analyze the variations in this one. So of course more number of parameters we can identify. So mostly so our aim is to determine the defect oriented way. So that's almost discussed here, and thank you so much for your kind attention. So is there any doubt you may ask?
Thank you very much, Kamalakkannan, for your wonderful presentation.
Thank you so much.
I will open the session for discussion. If the participants has any specific questions to ask, or please feel free to discuss now at this moment. If you are comfortable, you can also type the questions in the chat so that we can ask the questions on your behalf.
Hello. Can you audible, Kamalakkannan?
Yes sir, I am audible.
Yes, Kamalakkannan, good morning. Actually, nice presentation you have given.
Thank you sir, thank you.
Even I think this presentation will help basic material researchers and as well as faculty members also. Okay, anyway, I think I would like to ask some few questions regarding the basics, what you share. Okay. So the first question I will ask the general questions.
Okay.
Even I have seen many Raman spectrum and literature.
Okay.
So in that spectrum they mentioned A21 band, A32 band,
Yes,
3/2 band.
Yes.
So they have mentioned some numbers in each band.
Yes.
So what it indicate?
Yes.
So how we have to represent the number?
Yes, of course. That's the. So I already shown here in the character table itself. See, this is the notation. Simply, the notation is called Millikan symbols. So where one is the if we see something is mentioned that A1, in the sense it's a symmetry. One is mentioned by symmetry, where A is the symmetry with respect to the principal rotation axis. If 2 is there, it's anti-symmetric mostly. So if similarly B and E, T, so everything you can see that one. And I already mentioned if G is there in a sense, for the centrosymmetry molecules it's a symmetry, and for U is anti-symmetry. So what is symmetry and anti-symmetry in the sense, if you are applying that as symmetry operations, so whether it is changed its position, which means it's whether it's reversed or not, like that. If it is reversed now -1, and if it is not reversed now +1, like that you have to identify easily. Simply it's a representation. Yeah.
One more thing, one more question in addition to this.
Okay.
So even I think, for example, the graphene samples, I think many of the research have been characterizing using the Raman spectroscopy, and also the composite using metal oxide with graphene. Actually, they made they recorded the Raman spectrum also. So after making that composite, so the different peaks and different modes are there. So how to identify whether metal oxides is there or not, and what is the structure of the metal oxides? So how to find out based on the modes?
Okay, so this completely depends on the vibration between the particular system what you are talking there. So that vibration modes, if you are getting, suppose if you are getting short peaks na, that's fine. If it is getting that broad peak na, it may be mixture of the two things is also available. For that case you have to separate that peak from that particular one, and we have to do the symmetry things as where hybridization happening, like that we have to do it. So most probably for the broad nature of the features na, of course it's suppose some kind of additions you are doing, something like that. We can especially we can specifically we can tell that simply the vibration modes, what is the frequency, so that stands for the molecular vibration, which means CO2 in the sense carbon oxygen vibration, particular frequency will be there, that frequency is available. If your peak intensity is something related to that particular one, that particular bond length simply will be there, so that material will be available, like that you have to. Otherwise there is no other things, which means diatomic molecule I told na, which means this means vibrated is related to the R value, only this vibration only represented that.
Okay, one more question. So you mentioned a numerical aperture in the second order. So what is the role of numerical aperture?
Yeah,
what do you mean?
Yeah, numerical aperture in the sense, I think in your in our what's that basic courses we studied, like the resolving power and resolution of the lens.
Yeah, the resolving power is a different. So what is it?
Okay. Well, resolving power is nothing but
numerical aperture. I'm asking. So what is the role of numerical aperture here?
Yeah, numerical aperture is almost it's a sign value of the what is that? Sign value of the lambda around, like that simply.
No, if the numerical aperture value is varying, so what will be the effect in the Raman spectrum?
If numerical aperture is value varying, you can't get that jet scan things, which means the resolution will become very less. So I mentioned that 0.5 micrometer is the resolution of my spectrometer in the sense. If numerical aperture is 0.7 in the sense, you can't identify 0.5 things. Okay, you can go with 1 micrometer only the diaphragm, which means it's diaphragmatically limited actually. So it includes the values from 0.5 to 0.1. So specifically I want to mention the focus point only, then particular focus only, what is the damage I have to identify. For that case the numerical aperture is very high in the sense I can easily, the resolution is very high, okay, which means numerical aperture proportional to the resolution, simply resolution is very high completely. So if it is not there, your resolution is not good. So if you are mentioning that I am focused in 0.1 micrometer, 0.2 micrometer, 0.3 micrometer, in a sense the difference is 0.1 only. So this is not possible actually. So even though if you get the data, it may be not correct one, because resolution is very minimum. So if numerical aperture is very high, your resolution will be very high.
No, actually what I asked you, so the numerical aperture related to the lens or the material.
Yeah.
So where you have to consider the numerical
respect to lens.
Respective lens.
Lens.
Okay, and also you mentioned different sources for analyzing the Raman. So you suppose actually how to identify the exact source, laser source for my sample, different samples.
Yeah, which means if you are giving the energy which exerted that material up to the electronic level, that's also not a good one. And as well as if you are giving that very lesser value is also not good one, because this is approaching. You see, I saw the one slide. Yeah.
So how to identify? So before going to the Raman, how to identify?
It's almost near to the absorption of your material.
So that is before going to the Raman, first you have to take the UV.
Yeah, take that absorption point of things and nearby laser. What is you have to better for you.
So first we have to find out the excitation wavelength. First we have to find out the excitation wavelength.
Exactly.
So the laser source should be lower than the excitation wavelength.
Exactly.
Okay.
Thank you very
lower
much.
than the sense wavelength is higher comparatively. Wavelength is higher, na energy is low. If you are giving higher that particular, I mean, if you are giving that 300 nanometer in the sense, it is higher energy. Of course, it's reached that electronic level also. So that's give the wrong things, which means you have to choose the excitation value and higher than that particular one. Don't go very higher value. If you go the very higher value, now of course 2 or 3 points, so which merge together and you can't identify more number of points. Even though it gives the Raman, you can interpret that one. But if you are interested 1200 only, here 1200 you can able to see. And 1600 around you can see the 1600, but intensity is very minimum. And these peaks are suppressed if you are taking that 632.
Okay. Thank you, Kamal.
Yes.
Thank you very much. Maybe there are a few questions in the chat. I will just ask one by one.
Okay.
There is a question from Raja. What is the purpose of second order scattering in Raman scattering?
Yeah, of course. You see, in our samples also, simply we can identify the disorder completely, and measure of disorder also you can identify by plotting that second order Raman spectroscopy. So I already told, which means in our material, okay, it's a carbon material, carbon vibrations is separated because of the breakage of the bonds. So if I want to identify that particular one, I have to go to the second order region. So if a second order region is identified easily, which means if I identify now after implantation or after irradiated, the more number of damage is created in the sense it gives the different, I mean, G band, D band something, that's what is that? That is mixed together and gives the separate peaks, and how much is the area of under the particular peak, that directly gives the 1 minus A normalization. We can identify the disorderness. Completely disorderness you can identify easily in the quantitatively. That's the main application for the second order.
Thank you. The next question from Jyoti. What is first order and second order Raman spectrum? Is it applicable to organic compounds or for inorganic samples?
Mostly inorganic material we have to use these things, especially because the second order, first order, of course, first order almost we have to identify the molecule structure, everything we can identify whether the molecule present or not. But in the second order, the case, so whether if you are considered that carbon relative things are mostly carbon relative things and disorderness you have to identify. That's the main things, mostly inorganic. Organic is not applicable, I think so.
Thank you very much. Next question is from Shweta. Why do we get less intense Raman peaks with lower wavelength laser?
Lower wavelength laser, less intense Raman peak. So if you need to get the higher intensity in the sense, you have to give the high power laser, and accumulation time and the excitation seconds, you have to increase that, you can get the high intense. But in low wavelength laser, in the sense, if you are giving the lower wavelength, in the sense, it's give that fluorescence effect, or otherwise some other features will be given. You have to, if you need a higher intensity, in the sense, you have to increase the power simply. That you can do it. So if you need low intense means, that's different.
Thank you very much. And the next question is how we can select laser if the molecule is fluorescent. Normally it will interfere with Raman spectrum, right?
Yeah, of course. If it is a highly fluorescent materials, it will interrupt. Yeah, it will interrupt, of course. High fluorescence materials, of course, it will be interrupt. That must be avoided.
Thank you. What does D and G bands in graphene means?
So D and G is completely diamond and graphite bands only. Usually it means it gives is represented the hybridization things in the 1200 1400 range. Furthermore, these D and G bands in the graphene things we don't know exactly. so that we are not working this case. Maybe it's diamond and a graphite band only people are using that.
Yeah,
we are not working
and
this.
yeah, I also would like to add, maybe tomorrow there will be the speaker who is very much expertise in 2D materials. So you will have a demo session tomorrow. So I strongly encourage the participants to attend the afternoon session for the 2D material based demo. Thank you. There is one more question.
Okay.
So explain the excitation wavelength and confinement effect.
So define the excitation wavelength and the confinement effect. Okay. So excitation wavelength in the sense, yeah, of course, if okay. So if you are giving the some kind of energy, so what happens in the sense it will be excited. Okay, fine. So yes, fine. If excited in the sense it is going in the higher resistor state and coming to the lower resistor state. That is the excitation. And confinement effect, okay, so that things we have to understand. Fine. So that we have to understand.
Yeah. And the final question, it is like, does Raman spectroscopy is complementary to infrared? Does it share the characteristics of infrared, or it is considered an area in the electromagnetic waves?
Yeah, it's of course Raman spectroscopy is complementary for infrared for the centrosymmetry molecules. Okay, so yeah, it can be for non-centrosymmetry molecules. Both are it's both are available. So it shares that particular things as, of course, both are the vibrating energy level. In electromagnetic waves is both are the infrared region only. Of course, that's Raman is scattered one, infrared is absorption between the vibration level. So which means you have to observe the infrared region only. So it is going in the virtual state and come back in the excited level of the vibration level. So what is the difference between the 0 to that particular excited level? So that is related to the IR, infrared region only. Infrared spectroscopy is complementary only. Yeah, for the centrosymmetry molecules, but non-centrosymmetry both are available. Even A1 LO mode is available for the Raman also and the IR also. So both the things will be there.
Thank you very much.
Thank you.
And
Thank you very much.
maybe, do you want to suggest any good reference books for Raman? Many participants were asking.
Yeah, of course. Satyanarayana on vibration spectroscopy, that book is there actually. The complete characterization table and how we can identify everything you can understand from this particular book. We are using that things also. Satyanarayana.
Please send us the details so that we will.
Okay,
we
sure.
are also trying to send few course materials for the participants at the end of the course.
Okay.
So we will try to take that. If you are able to type it in the chat, maybe
sure.
all the participants will be able to view it. Thank you so much.
Thank you so much, ma'am.
There is a final question.
Okay.
Can 785 nanometer solid state diode laser die out all at once? I don't know what Shweta wants exactly to ask.
A general question, okay. Can 785 nanometer solid state diode laser?
Yeah, hello, sir.
Yeah, yes, ma'am. Yes.
Yeah, sir. Actually, a few days back when I was working,
Okay.
like with 85 nanometer solid diode laser,
Okay.
it happened to die out all at once. I mean, like generally, what it should happen, what we expect is like the intensity should go gradually, right?
Okay.
But then
Okay.
we found out that suddenly the power has decreased a lot
Okay.
one
So
night.
that's
So yeah.
okay, fine. That's fine. That's what is that? Simply, so you are mentioning that the laser power is decreasing in this way, like in LED
Yes.
principle. It's a semiconductor principle completely. You know, even if you are using the LEDs also, if there is any fault in this particular system, now the intensity will decrease gradually and it switch off like that. No power
Yeah.
comes. So something like that, which means so this is the principle of the semiconductor, like that, because you are using the solid state, the depletion region and separation of the carriers and recombination will give the lasers in the same coherent value. So maybe that LED, that semiconductor what you are using, maybe it in some damage. You have to change that. Usually it will not fall out. But if it is happening now, of course the solid state, simply the semiconductor is somewhat it's in damaged. Maybe the carriers which is produced are majority or minority carriers recombinations, maybe some kind of suppressing.
Okay. Okay, thank you, sir.
That may be the issue. Okay.
Yeah. That means like, yeah, there is no specific lifetime for such solid diode laser, right?
Yeah, of course. That's we can't mention that things actually. So we can't mention exactly. We can mention.
Yeah. Okay. Thank you, sir.
Thank you so much.
Thank you very much, Kamalakkannan, and it's really so good to have you here today. Thanks again. And I also would like to extend heartfelt thanks to all the participants who are like thoroughly engaged, and it's amazing to have you all.
Thank you, ma'am. Thank you so much.
Thank you. Thanks again.
Thank you, ma'am. Thank you so much. Thank you.
James, what's the exact?
Hello?
Yeah.
Can you hear me?
Yes.
Yes, ma'am. So, yeah, it is time to start to introduce Aaivalayam now. But, okay.